All right, let's take a quick look here, short little intro to something. What if you were trying to take, you want to add up the area under the curve, how about from, that looks easy enough, doesn't it? So your u substitution might be something like u equals x squared or something, right? Okay, we can do anything we want to do and it's not going to work. Okay, this is an example. There are some of these that exist. There are some examples of elementary functions that do not have antiderivatives that are elementary functions. So there is no antiderivative of sine of x squared. There's nothing whose derivative is sine x squared. Okay, and there's no way around it. There's no tricky technique of integration that's going to allow you to solve that. Another one would be something like, I think if we did square root of 1 minus x cubed, I believe that's one. Can't do it. Can't do it analytically. There's no antiderivative to that. But we have another option, right? Remember the stuff we did earlier with finite sums, right? We were able to make estimates of areas under curves that way too. Okay, but if we're going to do finite sums, let's at least do this in a way that's going to be where we can be more systematic about it. We don't have to reinvent the wheel every time, and it's going to be a little more efficient, right? So let's say we want to do something like, for example, well, let's just take, I'm just going to make a generic one. Let's just do f of x. So what if we go, we're going to be on number 8. Say we got something like that. Actually, it can be a little trickier than that. Okay, so let's say we want to go from A to B, right? And we're going to partition this into n partitions. But the problem here is that you might be thinking, well, problem solved. We'll just do what we did before, where we'll partition it into n rectangles and let n go to infinity. But what do you think is going to happen? If these functions don't have antiderivatives, do you think we're going to be able to take a limit as n approaches infinity? No, we're not, right? So, great idea. I can tell you're all having that idea, but it's going to fail miserably. Okay, so what we are going to do though is we're going to have to be able to pick a finite number of these that's going to give us a good enough approximation, right? So if we partition this thing up, now let's do that. Let's break this up into n partitions, right? Like so. What kinds of shapes could we use? Okay, we could use any number of different shapes. And this is a good model for what you have to do when you are, for example, writing computer code to try to make, to try to model something, right? We could be really sophisticated and we could choose our pieces to be sort of weird shapes that have vertical sides, horizontal bottom, and the top, we could turn the top into a quadratic fit of the function. We could take 3 points and we could actually do a regressional analysis and do a quadratic fit of the function. But to do that, and that's actually called Simpson's rule, if we do that, or we could make it cubic if we wanted to be even more sophisticated, but it makes the algorithm pretty hard, right? It's going to make finding the area under that curve for each one of those shapes is going to be a difficult formula or algorithm, right? Which makes the integral harder to do. The plus side is we could get a really accurate result with fewer of those shapes, right? But each one of them is going to be harder to calculate, okay? So what about plan B? Plan B, what if we did something that's a relatively easy geometric shape to use, right? We can for which we can calculate an area easily. So if the top, instead of making that quadratic, what if we just made it linear? Well, what do you call that shape? It's a trapezoid. Yeah, it's a trapezoid. Trapezoids are easy to deal with. Areas of trapezoids are easy to calculate, right? It's a geometric rule. It's, you know, we don't have to do anything fancy there. We don't have to do any weird functional analysis. We can just make it a trapezoid and add those up. But trapezoids are a lot better than rectangles, aren't they? Because trapezoids fit the curve pretty well. If it's a rectangle, we're inherently, if there's a slope at all, we're going to be missing a little bit, right? And we want to be efficient. We want to take the same number of geometric shapes, but make those geometric shapes match the curve as well as possible. So trapezoid we have, right? Okay, so let's think about this then. If we want to add this thing up, let's just look at each of these trapezoids and let's come up, like we did before, with an algorithm for just adding up the area under a curve for n trapezoids. And then that's what we're going to call the trapezoidal rule, okay? So what is, first of all, what's the area of a trapezoid? So let's just look at a generic trapezoid for a second. So if this is a trapezoid, what's the definition of a trapezoid? What are the characteristics of a trapezoid? Two sides that are parallel and two sides that are non-parallel, right? So if we want to find the area of a trapezoid, the way I would always encourage you to do this is to just play a movie in your head. You want to think geometrically. Can we tweak this shape in a way to make the area easier? Just like we did when we did the mean value theorem for integrals, right? Find the average value of a function. We brought in the calculus grinder and we ground down the function to make it rectangular, make the area rectangular, right? So that same area. Well, same thing here. How could I cut and slice and move pieces around here to make it rectangular? Sure, okay, so if we took the midpoints of both of those segments, right, then all we'd have to do is make a cut there and spin that piece around to fill in that spot, right? And then the same thing here, agreed? You could make that cut, rotate that around to fill in that one.
Or you could just count one side.
Well, but maybe not though, because they might be different slopes, right? They look pretty similar here, but they could be dramatically different.
So you never want to cut off the big side for that other?
Well, you can't generally do that, but we can always do this, right? So what does this do then? So if the parameters for the original trapezoid are, that's the height, right? And we're going to call this, we'll call this base 1 and base 2. What are they going to be the parameters for the rectangle? Well, the height stayed the same, didn't it? Okay. What happened to the lengths of the sides? 2 inches. Yeah, it's going to be, isn't it just going to be the average of the two? Would you agree? Because the midpoint, would you agree that the mid-segment, if you go back to geometry, the mid-segment of a trapezoid is equal to the average of the lengths of the two bases, isn't it? Does that make sense? Right? And so really this is just equal to the width of this thing is going to be the average of the two, and so we just end up with h times, how would we say the average of the two bases? Well, b1 plus b2 over 2, right? And so there's our formula then. You probably, the way you've seen that is 1/2 times b1 plus b2 times h is probably the way you saw that, right? But that's where we get it, right? Either way, it's not hard to do, right? So for us, then, well, these would be the bases, wouldn't they? And the height would just be, what would we call that? The width, what do we call the width of these segments? Think back to the finite sum stuff. We've got n segments in the interval from A to B. Well, okay, but so what's delta x equal to? We always called it delta x, right? Don't try to remember it, just think about it in terms of what it needs to be. If this is the total width of the interval, b minus a, and we're going to cut it into n sections.
So b minus a.
Yeah, b minus a over n, right? The total width divided by the number of sections gives me the width per section, right? Okay. So then that's going to be, that's the height that's just going to be our delta x, right? And b1 and b2 are just going to be the heights of each side, but those are determined by the values of the function, aren't they? So if I go out to the ith subinterval, well, that's delta x. What's going to be the height right there? It's determined by the value of the function on the right side, isn't it? So what's that gonna be then? F of,
Delta.
well, okay, so this is delta x, but remember, this is, so like, delta x is the distance between x sub I minus 1 and x sub I, right? Because x sub I is just, this is x sub 0. A is the same thing as the starting point, or x sub 0. So we take one step over delta x and we're at x sub 1. Is this ringing a bell? Then we get x sub 2 all the way over to x sub I, right? So x sub I is really just equal to a plus I delta x, right? And this one would be a plus I minus 1 delta x, right? So this is just going to be f of x sub I, which is a plus I delta x, right? The right base. And the left base is just going to be f of a plus I minus 1 delta x, right? So can you see, we just have a couple minutes, don't we?
Yeah.
So for now, can you see that we're going to be able to do this, right? We're going to be able to come up with an area of the trapezoid that's just based on what are the parameters going to be. They're just going to be a and b, right? So the limits of integration, and delta x, which is really just dependent on the number of trapezoids we're choosing, right? And then I'm just going to, I'm going to come up with some argument based on that I'm just going to plug into whatever the function is we're dealing with, right? Okay? Does that make sense? All right, so we'll pick that up tomorrow. We'll go a little further with it. But that gives you the basic ingredients of what we're going to do.